In this section, we're going to talk about the atmosphere. So there it is, the line between the Earth and space, clearly visible from the International Space Station. But does it lie at the Kármán line, the marker where space begins, or does it transition from the Earth to space more gradually? Well, let's dive in and take a look at everything to do with the air above our heads. What is it made from? Well, by composition, most of it is nitrogen at about 78%, and a smaller amount, 21%, oxygen. That's very important to us because when we breathe in both the nitrogen and the oxygen, it is the oxygen that our body needs. It's also made up of significant amounts of water vapor. When we look up at the nice blue sky and we see those clouds, we're always reminded that there's a huge amount of water up there. But also things like argon, carbon dioxide, etc. And you can see here all of the molecules and atoms that is in the air that we breathe every single day. But on that subject of why is the sky blue? Well, it turns out that blue light is scattered more readily than the longer wavelengths. So red, orange, and yellow, for example, they can travel through air without their path being interrupted by the air molecules. But the shorter wavelength blue light tends to scatter off the air molecules, and so what happens is the light starts bouncing around, and so when we look up at the sky, we not only see the light source, the sun, but we also see all of the sky around the sun glowing blue, all of that blue scattered light. Here's a photograph of me with a cyanometer, and the cyanometer measures the color of the blue sky. It helps to indicate just how much water vapor is present. When there is more water vapor, the sky turns whiter and whiter until eventually the sky can be completely white. So if the sky is blue, why are sunsets and sunrises red? Well, here's an important distinction. When the sky is blue, the sun is normally straight over our heads. The amount of atmosphere the sunlight has to get through, the line of sight is quite small compared to when the sun is low down near the horizon. There's just more atmosphere down there. You're looking through a larger slice of atmosphere. Now, over short distances, it is the blue light that gets scattered the most, but over longer and longer lines of sight of atmosphere, more and more of the longer wavelengths get scattered out until it is just the red light that remains. That means the sun becomes red as it sets behind the horizon, and the air around it is glowing red with scattered long wavelength light. Now, one thing you can see whilst observing a sunset is this, the green flash. Now, I think I've only seen this probably once, so it's quite rare. You normally see it when the sun is setting into the ocean. As the sun is in its final moments, what you'll sometimes see is bands of refracted light that make the sun appear to almost, rather than be spherical, it creates almost like a square top, and these bands shrink inwards as the light passes between these boundaries of the air. And as it shrinks inwards, at that final moment where it's about to disappear, the yellow light of the sun turns green for a split second, a green flash, one of the rarest sunset phenomena that you could ever see. So looking up into the sky, we are permanently reminded that the water cycle is active and busy, with the evaporation of water off the oceans, the transportation by winds of those clouds across to the land where precipitation falls out, landing on the ground, forming rivers and streams, and then running back into the ocean again, the constant cycle that we call the water cycle. Now, a big half of this at least happens in our atmosphere. The other half goes either across the land or under the ground. But it's a very important thing that our atmosphere is doing, constantly cycling the water on this planet. And clouds are very interesting. The more you look, the more things you see. And so this whole area of science is called meteorology, the science of understanding the weather, the changeability of our atmosphere. You see, we get different clouds, and these are basically clumps of water droplets or ice crystals that have become visible against the blue sky because of the way that the light is interrupted by those crystals or droplets. And so some of them we cannot see the sun through. Some of them we can. If ice crystals, higher clouds, cirrus clouds, uh, stratus clouds, these ones you normally be able to see the sun through because the ice crystals are quite far apart. As they get lower and lower clouds, eventually the water droplets, instead of ice crystals, they become so close together that the light from the sun gets completely scattered and interrupted. So you physically cannot see the sun through them, but they glow with the sunlight that has entered in. The scattered light that is coming from within the cloud makes them white and visible. Now, this is not the only place where we might find water in the atmosphere, because the blue sky, in the absence of any clouds, is still full of water vapor, but that water vapor has no distinct shape. It is just a gas. It is only when it has formed an aerosol or a suspension of ice crystals that we see it as a cloud. Now, of course, some of these ice crystals can grow in the clouds. That is how we get snowflakes. Some of the water droplets can freeze in the cloud, and that is how we get hail. If neither of these two things happen, then what we can get is the water droplets physically falling out of the clouds, and that is how we get rain. So if the clouds we can't see through are the clouds that are lowest in the atmosphere, if we wanted to see beyond our atmosphere, say into space with an observatory, then we need to get above those low-level clouds. And in fact, that is what we have done when picking the sites for the building of very large observatories. We normally go above that low cloud layer. So some famous ones for you: Palomar and Kitt Peak in America sit at the 2,000 meter mark or thereabouts. The Roca de la Muchachos Observatory in La Palma, one that I have been to and used, is at 2,396 meters. The Very Large Telescope in Atacama Desert, Chile, 2,600. And Keck, which sits on top of Mauna Kea in Hawaii, sits at an astonishing 4,000 meters above sea level, bringing it high above all of those low-level clouds. There's another good reason, though, why we'd like to put our observatories on the top of mountains, and it's the seeing. Now, seeing is about the turbulence of the air. Even if the air is transparent and see-through and without clouds, it might be that it's moving and shimmering in a way that ruins our view. If we are behind a mountain and the airflow is going across over the top of the mountain, then the seeing in that observatory is terrible. It's actually much better at the very top of the mountain where the turbulence is the least. What we also find is the seeing is weather dependent. When a new weather front comes in, the seeing is terrible because of all the turbulence. And what you'll find is just before a weather front coming in, when the air has calmed down and had the longest time to settle down from the last weather front passing over, that is the point where the seeing is the best. Another thing that might ruin our view is, of course, light pollution, because the atmosphere not only scatters light coming in from space, it also scatters light that would otherwise be trying to escape. Street lights and building illuminations actually sends light up, and not all of it completely clears the atmosphere. Some of it is scattered by the atmosphere, making the atmosphere glow. So if we want to get the best site for an observatory, we should build it away from bright cities and lights. Ports, for example, have very, very bright illumination, but they spoil the sky for many, many miles around. And so we need to get into a dark site for us to have the best chances of observing the cosmos. So let us now plunge in and have a look at how we divide our atmosphere into these different regions, starting with the troposphere, which is the bit of the atmosphere that we inhabit, and above that the stratosphere, the mesosphere, thermosphere, and exosphere. We're going to look at these one at a time, but familiarize yourself with the kind of scales that we're looking at here. So up to about 12 kilometers, that's the troposphere. Beyond that to 50 kilometers, a much bigger chunk, that's the stratosphere. A further 40 kilometers above that, that's the mesosphere. The thermosphere carries on for hundreds of kilometers, and the exosphere for thousands of kilometers. So basically, it is like an onion of layers of atmosphere, but the slices are getting thicker with each successive sphere. So for anyone that's climbed Mount Everest, you'd know that there's no air up there, or there's not enough oxygen. Well, this is not precisely true. There's still the same proportion of oxygen to nitrogen as there is down here. What there's less of is atmospheric pressure. So what happens is the pressure that the air exerts when it collides with like the walls of like your lungs, for example, it impacts with a certain amount of force, and your blood pressure basically pushes back the opposite way, and so they're in balance. If you go up a mountain too quickly, then the air is not bouncing off the insides of your lungs hard enough to overcome the force of your blood pressure, and so your lungs start to fill with fluid, and that's not ideal. So if you're going to go up somewhere like Everest and you want to go up quite rapidly, what you have to have is supplementary oxygen at atmospheric pressure. As we go up, the air pressure drops off lower and lower and lower until we get into those tenuous reaches of the upper atmosphere where the air would not be good enough or carry enough air pressure for us to breathe. Another issue, of course, is that it gets colder as you go up through the troposphere, and that's because we're getting further away from the ground. Now, the ground is a great big reservoir of heat. The sun is heating up the ground and the sea all the time, and so the air in direct contact with it gets warmed by that proximity. The further you go up, even though the light is passing through you, it goes through that air without imparting its energy mostly, and it's only when it hits the ground that the energy gets absorbed. And that means that when you're far away from the Earth, you're not receiving that heating effect from the Earth. So before we had pressurized aircraft, pilots had to go up with thick thermal layers on to keep warm because the temperature rapidly went down to -30, -40, temperatures likes of which we would only see at the poles. So let's depart the troposphere and enter into the stratosphere above. Now, the stratosphere is separated from the troposphere by a difference in the temperature. Whereas the temperature goes down as we get higher into the troposphere, suddenly the temperature starts to rise again, and that marks the start of the stratosphere. It's this region where the temperature starts to increase with altitude. Yes, the pressure continues to go down, but the temperature starts to creep back up until it's actually quite warm. Low pressure, but warm. And this is because at this layer we have the ozone layer, where O3, so an oxygen molecule containing 3 oxygen atoms, starts to absorb ultraviolet radiation from the sun. And in doing so, it turns into thermal energy and vibrates around, making those atmospheric molecules have more energy, and so be higher temperature. So in the stratosphere, if we launched a weather balloon, it would probably go all the way up into the stratosphere, and it would measure perhaps the temperature getting less and less and less, and then you would go past this tipping point, which is the start of the stratosphere, where the temperature now starts to increase and go up and up and up. There are some things of the stratosphere that we can see from the ground. The very highest of clouds lie on that boundary between the troposphere and the stratosphere. And there are, in fact, some extremely high altitude clouds. The Noctilucent clouds are very, very high altitude clouds that sit so high that they're normally illuminated by the sun when the earth below and the atmosphere below is in complete darkness. Sometimes called night shining clouds. You see them in the summer. They tend to be more to the north, and so sometimes called summer aurora, but nothing to do with aurora before. They're just very, very high altitude clouds picking up light from a sun that is well over our horizon. And up there in the stratosphere, any moisture is locked away in thousands and thousands of tiny little ice crystals. Now, the sunlight shining through those ice crystals can get up to some tricks. It's possible to see amongst those ice crystals halos and arcs and sundogs and lots of other phenomena where we basically see the light refracting through those ice crystals and being angled towards us by the shapes of the ice crystals in a particular way. The picture at the top is one taken at the North Pole. When you're in very cold places, you tend to see it better. The one underneath it, though, is my photograph that I took this year. You can see that it's got a very interesting effect, that it's like a double halo. The inner halo is quite a common feature, but the secondary halo is very rare indeed. Now, another thing that you might see at certain days of the year is some of the very high altitude clouds that normally sit above the North Pole may slide off the North Pole and be visible from places like the United Kingdom. Now, these are called nacreous clouds. These nacreous clouds have an opalescent, mother-of-pearl, oily even, distortion of colour. Now, this photograph at the bottom is one that I have taken a few years ago. I remember one in the 90s where the cloud was so vibrantly mixed in colour, it was like the reds and the greens of the cloud had completely separated. An absolutely incredible thing, but always worth looking up to see if you can spot any nacreous clouds. Have you ever seen a shooting star? Well, these shooting stars occur when a meteor, a very, very small asteroid, if you like, hits our upper atmosphere, and it hits so fast that the friction between the little rock and the air causes the rock to heat up to the point where it basically burns away to nothing. Now, in the process of burning up, where that happens the most, the peak heating is in the mesosphere. It's above the stratosphere. As the little rock goes through, it will leave a trail of highly ionized gas that boil off from the melting meteor. Sometimes they're green, especially if they are a bolide fireball. They're very, very green. Normally, as a kind of flame test to indicate things like magnesium and other chemicals present in the rock itself. So meteors, normally they burn up entirely within the mesosphere. Occasionally, they can make it all the way through, fall through the stratosphere and the troposphere, and land on the Earth as a meteorite. There's not very much else we can see in the mesosphere from down on the Earth, and that's because there's no great clouds that appear in the mesosphere. But what you can see in some very dark locations are gravity waves. Now, when there are very large storms that are perhaps beyond the horizon to you, they shunt the air up and actually create compressions that travel out from that storm as waves. Now, in very, very dark places, the slight sky glow can actually be affected by those ripply waves, so that you see a ripply pattern in the sky glow that would otherwise be there. And this actually happens right up in the mesosphere. Take a look at this exceptional image. Shout out to Stephen Hummel who took it. This is an incredible phenomenon. Even though a cumulonimbus cloud is basically based in the troposphere, with the top of it just peeking out into the stratosphere, way above in the mesosphere we get some optical phenomena associated with lightning. As the lightning strikes downwards, a jet of red light goes upwards. It's only there for a fraction of a second, normally too quick to see with the naked eye. I mean, it was reported by some pilots flying in the dark. They saw these flashes of red when traveling really high. But with long exposure photographs, we can pick them out. They look incredible. They are a huge burst of electrical discharge going upwards, normally red, exciting the same molecules as Aurora might in the very high atmosphere. And also, we've even managed to now photograph this from the International Space Station. An incredible thing. Normally what you need is thunderclouds beyond your horizon, and we need to look immediately above them. The thermosphere. So above the mesosphere, the thermosphere, it's a place where the temperature is very high, but the gas is extremely, extremely low and tenuous, like the air pressure is almost zero. But of the molecules that are there, they have been highly ionized by the ionizing radiation coming from the sun. And within this, there sits a band of the thermosphere that we call the ionosphere, because it's made of ions between 60 and 1,000 kilometers up. Now, this is where the solar radiation has ionized all the atoms and molecules, but it also creates a layer of charged particles that reflect radio waves. And so what it means is that if we had a radio broadcast, we could reflect it deliberately off the ionosphere so that it could travel around the curvature of the Earth. And strange enough, AM radio on an old-fashioned radio use exactly that. It was basically a radio signal that we bounced off the ionosphere, allowing us to hear signals from around the world. And what we find in the day, when the solar radiation is stronger, there's more ionization, and this creates a denser lower level, which means that our signals do not go very far. But at night time, the lower level is not so dense. The signals bounce off a higher level of the ionosphere, which means they actually have the capacity to go further around the world. It means that if you had an old-fashioned radio and you tuned into an AM station, in the daytime you might just hear snow, like, but at nighttime you're getting Radio Gibraltar or something like that. You're getting radio signals from much greater distances. And up there in the thermosphere, we also see the Aurora. Now, to get an idea of what causes aurora, we must go way out of Earth for a second and look at the Earth-Sun system. The Sun is forever giving off something called solar wind, highly ionized charged particles accelerated away from the Sun and blasted towards the solar system. Now, our own magnetic field around the Earth protects all of the lower latitudes around the equator from these particles from entering. The charged particles get steered sideways by the Earth's magnetic field so that they don't reach the surface of the Earth. But of course, above the North and South Pole, there is this opening, a weakening point in the magnetic field where charged particles can get trapped and spiral down towards the Earth. Now, as they are, these charged particles are invisible to us. But when they hit the Earth's thermosphere, really high up, they excite the oxygen and the nitrogen molecules that are there, making them give off their characteristic wavelengths that we see when those gases are excited. Do you want to see some pretty pictures? Let's have a look. And here we have the aurora seen above the school in which I work, and two different situations. You can see that it's pink and green, and then it comes down in shafts and it flickers and changes, kind of looks like curtains. Now, normally this is seen in a ring around the North and South poles, roughly at the sort of latitude of northern Norway and Iceland and Canada. But occasionally solar storms can send out a very large number of charged particles. The magnetic field gets distorted by this blast, and so aurora can occasionally be seen further south. And so that is exactly what happened in these situations. If you hear of aurora that's about to happen, get out there and have a look. You just need a dark sight, look at it with your eyes. It is magnificent. And as you can see, I got quite carried away. And an important thing to note is, unless the site is very dark, the aurora will be in black and white for you, because the black and white receptors in the retina of your eye are more sensitive than the color ones. It has to be very, very vibrant aurora for your eyes to pick out the color. In this particular storm, the whole sky was full of aurora, and so you could see the color quite easily. Three types of aurora that I want to bring to your attention: the aurora borealis, which is the aurora that occurs in the northern hemisphere, the one that we have the greatest experience of because people have inhabited those places since people first spread into Europe. Whereas the aurora australis, which is the southern lights, is generally only seen occasionally in places like New Zealand and Antarctica and the Southern Ocean, where people actually rarely go. It is something that illuminates the South Pole quite regularly, but at the same time is very rarely actually seen by people because there's no great land masses down there. Another thing I want to mention is Steve. Steve, who is a very strange name, is the name given to the most recently discovered phenomena within aurora. It's a narrow purplish streamer ribbon in the sky, often seen near aurora, like in this picture here. They didn't know what to call it, so they called it Steve. What a great name. So going out beyond the thermosphere, above the aurora, and heading out for thousands of kilometers into space for many times the radius of the Earth is the exosphere, the escaping gases that basically make the region around the Earth richer in atmospheric particles than deep space. We can't see it basically from the Earth. We can find it very difficult to detect anywhere, but this photograph here, taken from the surface of the moon, an ultraviolet photograph, can show clearly that the Earth has got a visible but very faint atmosphere spreading out for several times the Earth's diameter into space. This is the exosphere. This is where the planet bleeds off some of its fastest moving molecules into deep space, and why space is not empty entirely, because it does contain some particles that have escaped from planets themselves. Now, a second ago, we talked about aurora, and there was a word on the screen there that I never described at the time, the magnetosphere. Now, to be clear, the magnetosphere is not a part of the atmosphere. It's not one of the bands as we go up. It's actually a description of the sphere around us that our Earth's magnetic field inhabits. It is the Earth's magnetic field. Now, the region around us is directly influenced by that rotating core of the Earth. It creates a field around the Earth of which the Sun's magnetic field cannot break in. However, outside of the magnetosphere, we get the sun's magnetosphere. And so at the boundary between the two, we get an interaction, and it is in this boundary that Earth's magnetic field moves along, and the charged particles come and get deflected. Some can creep in the poles because that's where Earth's field density has got like basically an opening for the charged particles to gain entry. Now, we knew for quite a long time that the magnetic field would be out there, but it took the launch of America's first satellite, Explorer 1, for this scientist, Van Allen, who had designed he designed a Geiger counter to be taken up on board the spacecraft to see what the radiation environment of space was like. They realized that over certain regions, the Earth's magnetosphere was full of highly ionized particles bouncing around that to us would be like radiation. And so these radiation belts were called the Van Allen belts. They sit there at a height greater than the International Space Station would fly. If we were to leave the Earth and go to the moon, you would briefly have to fly through these radiation belts. But generally, any spacecraft that has got tin foil or is made out of aluminium would be screened against these kind of charged particles. But we do have to be careful with some of our spacecraft, especially if there's a solar storm. It can excite the radiation belts and overload some of our satellites. Now, because of the shape of the Van Allen belts and because of underlying magnetic rocks, there's a region where the radiation zones actually reach down through the atmosphere and touch the Earth. And this is in the South Atlantic. It's something called the South Atlantic anomaly. Now, you can't detect it normally, but our satellites tend to travel through this region and go through a region of greater radiation. In solar storms, when Earth's magnetic field is buffeted, we might find that this extends further down all the way to the ground and could interfere with compasses. Now, a hypothesis has linked the disappearance of boats and aircraft in the Bermuda Triangle immediately to the north with the South Atlantic anomaly, that a solar storm pushes the radiation belt down into the Earth's atmosphere, it changes the magnetic field lines, airplanes start that are following a bearing, flying round and round in circles. And so this is a possible explanation, better explanation than abducted by aliens. Now, our atmosphere does many things for us. It gives us the oxygen we breathe. It holds the carbon dioxide that plants need. It also keeps us warm. It holds greenhouse gases like water vapor and carbon dioxide that basically keep the Earth at a nice temperature for life to exist. But the atmosphere does some other things. High up, those gases actually block harmful types of radiation. In fact, there's only certain windows in the electromagnetic spectrum where light can reach the surface. Visible light is, of course, the most obvious. Our eyes have evolved to accept the light that reaches the surface of the planet so that we can gauge the most information about the world around us as our senses will provide. There are a few narrow windows of infrared, but these basically get blocked by water vapor in the atmosphere. So if you can find a place nice and devoid of water vapor, then you can see out in the infrared. But mainly then it's just radio waves after that. Radio waves reach the Earth's surface from space, and we can broadcast out into space using radio waves. All of the gamma rays, the X-rays, and the ultraviolet are blocked by our atmosphere, which is a good job because these ionizing radiations would be harmful to us. And you can see there's a blockage in the sort of high infrared, low microwave region as well. There's another place where our atmosphere is not transparent. Those waves get absorbed. So here on the Earth, we try to take full advantage of those windows out. We can see out in visible light. You can see the Keck telescopes there. And we also, in places where there's very low atmospheric water vapor, we can look out in the infrared. At the South Pole, there is an infrared telescope. We can also study the universe from the ground with radio waves. There's John Wallbank telescope, which is in the UK, and so we can see what the universe is telling us in the wavelength regimes of the visible light, radio waves, and in some places infrared. The best place for seeing infrared above the clouds is perhaps not on a mountaintop, but even higher still, and that's what they did. They attached a large telescope into the fuselage of a 747, and they can fly it really high in the atmosphere above most of the water vapor, allowing them to take some really, really interesting infrared images of space. Now have a look at this. This is the Horsehead Nebula. You see some glowing gas with a dark globule of gas in front of it. Looks like a horse's head. Well, in the infrared, it is those dark globules that actually glow with a sort of a warmth that can be detected only in the infrared. If we want to see what the universe is telling us in any other wavelength, we've got to go above the atmosphere. See all of these spacecraft detecting things in various different wavelengths of light that our eyes can't see. I have used several of these spacecraft to take observations, looking at what the universe is telling us in gamma rays, in X-rays, in ultraviolet, and in the microwaves. We can't detect these from the ground, so we launch these telescopes into space where they operate robotically as satellites. And the clearest view possible is not only in space, but far away from the Earth. Here, the James Webb Space Telescope looks out at deep space in the infrared to look at dust and gas and stars that go right the way back to some of the earliest galaxies in our universe. And here, the breathtaking view, a close-up of the region near the Horsehead Nebula, where clearly we can see a galaxy full of stars, and in the near ground, a cloud of gas from which stars will eventually form. Images that we could not get sitting in an observatory at sea level next to a city behind a mountain. We have taken our observatory to the place where the seeing is best, the conditions are best, to maximize the potential to do great science.